darkness between stars, something 7 billion years old has been drifting toward us since the dawn of recorded history. This ancient ice bomb, moving faster than any natural comet should, carries toxic chemicals we've never seen before. Scientists call it the third interstellar visitor, but some warn it could be something far worse. On October 29th, everything could change when it reaches maximum solar heating and we lose sight of it behind our sun. The countdown has already begun. Prepare yourselves. We dive into the worst-case scenario. A frozen relic, older than Earth itself, has entered our solar system, and it carries secrets from a time before our sun was born. When astronomers first spotted this visitor on July 1st, 2025, they realized they were looking at something extraordinary. Designated as the third interstellar visitor, it has been traveling through the void for 7 billion years. To put that in perspective, our entire solar system is only 4.6 billion years old. This wanderer was already ancient when the first rocks began forming around our young sun. The comet originated from the galactic thick disk, a region of our galaxy populated by the oldest stars in the Milky Way. These stellar ancestors formed when the universe was young and heavy elements were scarce. The fact that this visitor comes from such an ancient neighborhood means it contains materials that predate everything we know about planetary formation. Scientists have never observed anything quite like it. Unlike comets born in our solar system, this traveler shows chemical signatures that seem impossible. Its composition tells a story of formation conditions that no longer exist anywhere in the known universe. The water ice it carries has been frozen solid since before multicellular life appeared on Earth. Think of it as a time capsule launched from cosmic dawn. While our solar system was still a swirling disk of dust and gas, this object was already fully formed and beginning its journey through interstellar space. It has witnessed the birth and death of countless stars, survived radiation storms that would sterilize planets, and endured temperatures just 3 degrees above absolute zero. The discovery came through the Asteroid Terrestrial Impact Last Alert System, a defense network designed to spot threats to Earth. The irony was immediate. A system built to protect our planet had found something that might represent the oldest matter ever detected in our cosmic neighborhood. The Atlas telescope in Chile captured the first images, showing a faint smudge moving against the background of stars. Within hours, astronomers worldwide were tracking the object, trying to determine its exact trajectory and composition. What they found defied expectations. This was no ordinary space rock. The preliminary observations showed clear signs of activity. Gas and dust streamed from its surface as solar radiation began to warm its ancient ices. The visitor measures somewhere between 1,000 feet and 3.5 meters across, though its exact size remains uncertain due to the surrounding cloud of material. Its surface has been bombarded by cosmic radiation for billions of years, creating a crust unlike anything in our solar system. As we track its approach, one thing becomes clear. This ancient traveler holds clues about the earliest epochs of cosmic evolution, but with those clues come risks we never anticipated. The same processes that preserved this relic for billions of years might now unleash consequences we cannot predict. Studying this visitor reveals something even more disturbing than its ancient origins. Comets always grow tails, pointing away from the sun. Except this one has broken the fundamental rules of physics. Every astronomy textbook teaches the same basic principle. Solar radiation pressure pushes comet material away from the sun, creating a tail that always points in the opposite direction. This has been observed in every comet throughout human history until now. This object displays what scientists call an anti-tail, a stream of material extending in front of it as it moves through space. The tail stretches directly opposite to where it should be, aligned toward the sun rather than away from it. This phenomenon has left astronomers scrambling for explanations. The most unsettling part is that this behavior suggests the presence of large particles, much bigger than typical comet dust. Normal comet tails consist of tiny particles, smaller than a human hair, that get blown backward by solar wind and radiation pressure. These microscopic fragments create the beautiful streaming tails we see in photographs. This visitor ejects particles so large they resist solar pressure entirely. Instead of being pushed backward, they maintain their forward momentum, creating a buffer zone ahead of the comet itself. These particles measure well above 1/1,000,000th of a meter, making them essentially immune to the forces that govern normal cometary behavior. The forward-pointing tail extends for thousands of miles, creating what appears to be a protective shield. When scientists first observed this formation through the Gemini South telescope, they thought their instruments were malfunctioning. No natural process should create such a configuration. The implications are staggering. If this object naturally produces large particles that resist solar forces, it operates by mechanisms unknown to science. The energy required to eject such massive debris should tear the comet apart. Yet it continues functioning as if nothing unusual is happening. Consider the scale of what we are witnessing. The anti-tail measures several arcseconds across when viewed from Earth, which translates to roughly the diameter of our entire planet at the comet's current distance. This suggests an active process far more powerful than anything observed in our solar system's comets. Some researchers propose that the forward-streaming material serves a specific purpose. The large particles could act as sensors, detecting obstacles in the comet's path and providing advanced warning of potential collisions. This theory suggests a level of sophistication that challenges our understanding of what natural objects can achieve. The timing of these observations adds another layer of mystery. The anti-tail became visible just as the comet entered our solar system's most dangerous region, the asteroid belt. This area contains over 1 trillion rocks larger than 65 feet across, any one of which could destroy or deflect an incoming object. The Harvard-Smithsonian Center for Astrophysics has published papers suggesting this forward-streaming behavior might indicate an artificial origin. If true, the anti-tail represents technology designed to protect an interstellar spacecraft during its passage through populated star systems. But the wrong direction tail is just the beginning of the anomalies surrounding this visitor. The very system that detected it was designed for a completely different purpose. The defense network that spotted this visitor was built to warn us about extinction-level threats, and it may have found exactly what it was designed to detect. On a clear night in the Chilean Atacama Desert, the Atlas Survey telescope was automatically scanning the sky for killer asteroids when it captured images of something that should not exist. The asteroid terrestrial impact. Last Alert System operates as humanity's early warning network. Designed to spot space rocks on collision courses with Earth, Atlas represents our most sophisticated planetary defense technology. 4 telescopes stationed across the globe work around the clock, photographing the entire visible sky every 2 nights. Their mission is simple: find any object that could impact Earth and provide enough advanced warning to mount a defense. The system can detect asteroids as small as 100 feet across, up to 3 weeks before impact. That might not sound like much time, but it represents the difference between global catastrophe and successful evacuation or deflection. Since becoming operational, Atlas has identified thousands of potentially hazardous objects, tracking their orbits with extraordinary precision. When the Chile station flagged an unusual moving object on July 1st, the automated systems immediately classified it as worth investigating. Within hours, follow-up observations confirmed something unprecedented. This was not a local threat, but an interstellar visitor traveling at impossible speeds. The discovery process reveals just how rare these encounters truly are. In over 20 years of systematic sky surveys, astronomers have confirmed only 3 interstellar objects. The first, discovered in 2017, was initially mistaken for an asteroid until its strange acceleration revealed otherwise. The second, found in 2019, displayed more typical comet behavior, but still puzzled scientists with its composition. Now, Atlas had found the third, and it immediately stood out as the most unusual of all. Unlike its predecessors, this object showed signs of complex internal activity from the moment of detection. Its brightness varied in ways that suggested active outgassing, while its trajectory indicated speeds far exceeding anything seen before. The irony runs deeper than just the discovery method. Atlas was specifically designed to protect Earth from cosmic impacts. Yet, it may have identified something far more dangerous than any asteroid. If this object represents technology from another star system, the implications extend far beyond planetary defense. Consider the timing of the detection. The visitor entered our solar system's inner regions during a period of unprecedented astronomical surveillance. 50 years ago, such an object might have passed unnoticed. Today, our defense networks ensure that nothing larger than a house can approach Earth without detection. The Atlas team followed established protocols, immediately sharing their observations with the Minor Planet Center and observatories worldwide. Within 24 hours, 31 different facilities had confirmed the object's existence and began tracking its trajectory. The data quickly revealed the visitor's interstellar origin. Its hyperbolic orbit showed it was moving too fast to be gravitationally bound to our sun. This was a true outsider, passing through our solar system on a journey that would take it back into the void between stars. But the defense system that found it has revealed something that defies every law of orbital mechanics. This visitor is moving faster than physics should allow. Racing through our solar system at 137,000 miles per hour, this visitor travels faster than any natural object should be able to achieve. When scientists calculated the exact velocity of this interstellar wanderer, the numbers defied explanation. Most comets from our solar system travel at speeds between 20,000 and 40,000 miles per hour when approaching the sun. Even the fastest recorded natural objects rarely exceed 60,000 miles per hour. This visitor maintains a consistent speed of 61 kilometers per second, which translates to velocities that challenge our understanding of gravitational dynamics. At this rate, it could travel from New York to Los Angeles in under 2 minutes. The energy required to maintain such speeds suggests forces far beyond normal gravitational acceleration. The object follows what astronomers call a hyperbolic trajectory, meaning its path curves so slightly that it appears almost straight. This trajectory requires an orbital eccentricity of 6.141, the highest ever recorded for any object in our solar system. To put this in perspective, most comets have eccentricities between 1 and 3. Think of it like a bullet fired through a crowd. While normal comets follow curved paths that bring them back toward the sun repeatedly, this object streaks through our solar system in what amounts to a straight line. Its path shows no significant curvature, despite the sun's enormous gravitational influence. The speed creates immediate practical problems for observation and study. Ground-based telescopes must track the object continuously as it races across the sky, making detailed spectroscopic analysis extremely challenging. Space-based instruments like the James Webb Space Telescope can only observe it during brief windows when their pointing systems can keep pace. More troubling is what this velocity means for the object's internal structure. Moving at such speeds through space exposes any object to constant bombardment by cosmic particles and radiation. For billions of years, this visitor has endured impacts that should have shattered any normal comet into fragments. The fact that it remains intact suggests either extraordinary durability or some form of active maintenance. Natural objects simply do not survive 7 billion years of high-speed travel through interstellar space without showing signs of severe damage. Yet this visitor appears remarkably preserved. Scientists have calculated that at perihelion, when the object reaches its closest approach to the Sun, it will be traveling at 68 kilometers per second. This represents the maximum speed it will achieve during its passage through our solar system, faster than any spacecraft humanity has ever built. The incredible velocity also means we have a very limited window to study this visitor. Unlike regular comets that return every few years or decades, this object will pass through our solar system exactly once. After its close approach to the Sun in late October, it will begin its journey back into interstellar space, never to return. Attempts to launch spacecraft to intercept the object have been deemed impossible. The energy requirements would exceed our current technological capabilities by orders of magnitude. We are limited to observing from a distance as this speed demon races past us. The high velocity presents another disturbing possibility. If this object is indeed artificial, its builders designed it to travel between star systems in reasonable time frames. This suggests a level of technological sophistication that makes our fastest spacecraft look like horse-drawn carriages. But speed is not the only anomaly this visitor displays. Its chemical composition reveals substances that should not exist. Analysis of the gases streaming from this object reveals a chemical signature that violates everything we know about comet formation. When the James Webb Space Telescope turned its instruments toward this visitor, scientists expected to detect the usual mix of water vapor, carbon monoxide, and simple organic compounds found in all comets. Instead, they discovered something unprecedented: an atmosphere dominated by carbon dioxide, with water making up only a tiny fraction of the total. Normal comets consist primarily of water ice mixed with rock and dust. When solar heating causes this ice to sublimate, it creates the familiar glowing coma and tail that make comets visible from Earth. Water vapor typically accounts for 80 to 90% of all gases released by active comets. This visitor flips that ratio completely. Carbon dioxide dominates its atmosphere to a degree never observed in any comet, interstellar or otherwise. The ratio of carbon dioxide to water exceeds anything in our astronomical databases, creating a chemical fingerprint that suggests formation under impossible conditions. The presence of such high concentrations of carbon dioxide implies one of two equally disturbing scenarios. Either this object formed near the carbon dioxide frost line in its parent star system, where temperatures would create mostly dry ice instead of water ice, or it has been exposed to radiation levels so intense that they fundamentally altered its composition. Scientists have also detected traces of carbon monoxide, carbonyl sulfide, cyanide gas, and atomic nickel vapor. This cocktail of chemicals creates an atmosphere more toxic than anything found in our solar system. Breathing air with similar concentrations would kill a human in seconds. The presence of metallic vapors particularly puzzles researchers. Atomic nickel requires extremely high temperatures to exist in gaseous form. Yet, this visitor releases it continuously as it moves through the cold of space. This suggests internal heating mechanisms that operate independently of solar radiation. Consider what this chemical profile reveals about the object's origin. If it truly formed 7 billion years ago in the galactic thick disk, it contains materials processed by the earliest generations of stars. These ancient stellar furnaces created heavy elements through nuclear fusion processes that no longer occur in our region of the galaxy. The toxic gas emissions also raise disturbing questions about the object's interaction with anything in its path. As it travels through our solar system, it leaves behind a trail of poisonous chemicals that could contaminate any spacecraft or celestial body it approaches closely. Spectroscopic analysis has revealed that the comet's coma extends outward for at least 216,000 meters, creating a vast cloud of toxic gases larger than the distance from Earth to our moon. This enormous atmosphere means the visitor's influence extends far beyond its solid nucleus. The chemical composition becomes even more mysterious when compared to other interstellar visitors. The previous interstellar comet, discovered in 2019, showed water and carbon monoxide in normal proportions. This new visitor represents something completely different, with a chemical signature that suggests either exotic formation conditions or artificial manipulation. Recent observations have shown that the comet's atmosphere is becoming redder as it approaches the sun, indicating changes in chemical composition or the release of different materials from its interior. This evolution suggests complex internal processes that remain active after billions of years in space. The implications are chilling. If this object represents a natural comet formed under conditions that no longer exist anywhere in the known universe, it carries chemicals and process that could fundamentally challenge our understanding of planetary science. But the most dangerous moment in this visitor's journey is rapidly approaching. On October 29th, everything changes. In less than 2 months, this ancient visitor will reach perihelion, the moment of maximum solar heating that could trigger events we cannot predict or control. Perihelion represents the most critical phase of any comet's journey. As the object approaches its closest point to the sun, solar radiation increases exponentially, heating the surface to temperatures that cause violent outgassing of frozen materials that have remained stable for billions of years. For this visitor, perihelion will occur at 1.36 astronomical units from the sun, placing it just inside the orbit of Mars. At this distance, solar heating will be 60 times more intense than what the comet has experienced during its 7 billion year journey through interstellar space. The temperature differential presents an unprecedented scenario. This object has been subjected to the background temperature of space, roughly negative 450 degrees Fahrenheit, for longer than our solar system has existed. Suddenly exposing such ancient ices to solar heating could trigger catastrophic outgassing events. Scientists have observed similar situations with comets from our own solar system. When long-period comets make their first approach to the sun after thousands of years in the outer solar system, they often experience violent outbursts as volatile materials rapidly sublimate. Some comets fragment entirely under the thermal stress. This visitor faces exponentially greater thermal shock. No natural object has ever experienced such extreme temperature changes after such an extended deep freeze. The rapid heating could cause the ancient ices to expand faster than the structural integrity of the nucleus can handle. The perihelion passage creates another critical problem: observation blackout. As the comet approaches its closest point to the Sun, it will pass directly behind our star from Earth's perspective. During the most active and potentially dangerous phase of its visit, we will be completely unable to observe what happens. This blind spot could last several weeks, depending on the comet's exact trajectory and brightness after perihelion. All Earth-based telescopes and most space-based instruments will be unable to track the object during the period when it experiences maximum thermal stress. The timing could not be worse. Comets often undergo their most dramatic changes during perihelion passage, sometimes increasing in brightness by thousands of times as massive amounts of gas and dust are released. Without continuous observation, we have no way to monitor whether the visitor remains intact or fragments into multiple pieces. Previous interstellar visitors have shown unpredictable behavior during a solar approach. The first detected interstellar object displayed unexplained acceleration as it passed close to the Sun, a behavior that still puzzles scientists. If this new visitor exhibits similar anomalous behavior, we might not detect it until it's too late. The October 29th date represents more than just a scientific milestone. It marks the moment when billions of years of stable equilibrium end, replaced by conditions that could fundamentally alter the visitor's structure and trajectory. Any changes to its path or composition during perihelion could have consequences that extend far beyond the immediate vicinity of the Sun. Mathematical models suggest the comet will reach its maximum speed of 68 kilometers per second during perihelion passage. At such velocities, even minor course corrections could redirect the object toward populated regions of the solar system. Weather and atmospheric conditions on Earth could also interfere with post-perihelion observations. If cloud cover or atmospheric disturbances prevent immediate reacquisition of the target when it emerges from behind the Sun, we could lose track of the visitor entirely. But thermal stress is not the only threat this ancient wonder poses. Its 7-billion-year-old structure might not survive the approaching solar encounter. 7 billion years of cosmic bombardment have weakened this ancient visitor to the breaking point, and solar heating could shatter it into thousands of lethal fragments. Comet fragmentation represents one of the most spectacular and dangerous events in our solar system. When a comet's nucleus breaks apart, it releases enormous amounts of stored energy while creating multiple smaller objects that follow unpredictable trajectories. This interstellar visitor faces fragmentation risks, unlike anything astronomers have previously encountered. Its nucleus has endured cosmic ray bombardment, micrometeorite impacts, and thermal cycling for longer than our Sun has existed. Such extended exposure would create fractures and weak points throughout its internal structure. The nucleus likely resembles a loosely bound rubble pile held together by gravity and frozen volatiles. As solar heating begins to sublimate the ices that act as cosmic cement, the structural integrity could collapse catastrophically. Instead of one predictable object, we would suddenly have dozens or hundreds of fragments following independent orbits. Historical precedent shows how devastating comet breakup can be. In 1994, Comet Shoemaker-Levy, 9 fragmented and crashed into Jupiter, releasing energy equivalent to millions of nuclear weapons. Each fragment created impact scars larger than Earth itself, visible for months after the collision. This visitor carries far more destructive potential. Its 7-billion-year accumulation of exotic ices and materials could release energies that dwarf the Jupiter impacts. The chemical composition alone suggests volatile compounds that could explode with tremendous force when heated rapidly. Fragmentation would also multiply the observation challenges exponentially. Instead of tracking one object through its perihelion passage, astronomers would need to monitor potentially hundreds of pieces, each following its own trajectory and displaying different levels of activity. The fragment distribution could create a debris field extending across millions of miles. Any spacecraft or celestial body passing through such a region would face bombardment by high-velocity ice and rock fragments traveling at interstellar speeds. Computer simulations suggest that if fragmentation occurs, the resulting debris cloud could persist for decades. Unlike fragments from solar system comets, which eventually either impact planets or get ejected into deep space, pieces of this visitor could remain in unstable orbits that periodically bring them back into populated regions. The exotic chemical composition adds another layer of danger to potential fragmentation. Each fragment would carry its own atmosphere of toxic gases, creating multiple sources of contamination, rather than a single manageable threat. Thermal stress analysis indicates the most likely fragmentation scenarios. Rapid heating during perihelion approach could cause explosive outgassing that literally blows the nucleus apart from within. Alternatively, differential heating between the surface and interior could create thermal shock fractures that split the object into large pieces. The visitor's rapid rotation, if confirmed by future observations, would add centrifugal stress to thermal expansion. Objects spinning rapidly while undergoing heating can tear themselves apart as internal forces exceed gravitational binding. Previous interstellar visitors provide little guidance for prediction. The first interstellar object showed no signs of fragmentation, but also displayed minimal cometary activity. The second interstellar visitor remained intact throughout its passage, but originated from much younger stellar regions. Fragment trajectories could scatter in all directions from the breakup point. While most pieces would continue on hyperbolic trajectories out of the solar system, some could be slowed by the fragmentation event enough to become temporary captives of solar gravity. The mass distribution among fragments could vary enormously. One large piece might retain most of the original mass, while dozens of smaller fragments scatter in all directions. Alternatively, the object could shatter into pieces of roughly equal size, multiplying the number of significant threats. But even if this visitor survives its solar encounter intact, it must navigate through the most dangerous region of our solar system. Its trajectory carries it directly through Mars's orbital path. This interstellar visitor will pass directly through Mars's orbit in early November, creating a potential collision scenario that could devastate the red planet. The orbital mechanics place this encounter in a cosmic game of Russian roulette. Mars travels around the Sun at an average distance of 1.5 astronomical units, following an elliptical path that brings it closer and farther from our star throughout its year. The visitor's trajectory intersects this orbital zone precisely when Mars could be approaching the same region of space. Collision probability calculations remain uncertain due to the exact timing variables involved. Mars completes one orbit every 687 Earth days, while the visitor follows its hyperbolic path at 61 kilometers per second. The intersection window measures only a few days, but the consequences of a direct impact would be catastrophic. An object measuring potentially 3.5 meters across, traveling at interstellar velocities, would strike Mars with the kinetic energy of billions of nuclear weapons. The impact would excavate crater hundreds of kilometers in diameter, ejecting massive amounts of Martian rock and soil into space. The impact energy would instantly vaporize any subsurface ice deposits at the collision site, creating a temporary atmosphere thick enough to be visible from Earth. The explosion would generate seismic waves that could trigger planet-wide Marsquakes and potentially destabilize the polar ice caps. Mars's two small moons, Phoebes and Deimos, orbit close enough to the planet that impact debris could pose threats to their structural integrity. Large chunks of ejecta traveling at escape velocity could collide with these moons, potentially fragmenting them or altering their orbits. The timing of this potential encounter creates additional complications for human Mars exploration. Multiple space agencies have robotic missions currently operating on or around Mars, including rovers, orbiters, and atmospheric sensors. A major impact would destroy these assets and set back Mars exploration by decades. Even a near miss could prove dangerous. The visitor's gravitational influence and outgassing activity could perturb Mars's thin atmosphere or affect its orbital parameters. The toxic chemical trail left by the comet could contaminate the Martian environment for years. The red planet's low atmospheric density provides minimal protection against high-velocity impacts. Unlike Earth, which has destroyed many incoming objects through atmospheric friction, Mars would absorb the full kinetic energy of a collision with minimal mitigation. Impact modeling suggests the explosion would be visible from Earth as a bright flash lasting several minutes. The debris plume could extend thousands of kilometers above Mars's surface, creating a temporary ring system around the planet. Ground-based telescopes and Mars orbital missions would provide unprecedented documentation of such an impact, assuming they survive the initial blast effects. The scientific value of observing an interstellar object collision would be immense, but the cost in terms of existing Mars infrastructure could be devastating. The gravitational interaction between Mars and the visitor could also alter the comet's trajectory slightly, potentially redirecting fragments toward other targets in the inner solar system. Even minor course corrections could have significant consequences over interplanetary distances. Orbital dynamics calculations show that the encounter will occur during Mars's northern hemisphere winter, when the planet's distance from the Sun is near maximum. This timing could influence how impact debris disperses and whether temporary atmospheric changes persist long enough to affect global climate. The European Space Agency's Mars Express orbiter and NASA's various Mars missions would need to implement emergency protocols if collision probability increases. Spacecraft could be moved to safer orbits or shut down temporarily to prevent damage from debris impacts. But the Mars encounter represents just one of several explosive scenarios this visitor could trigger. Ancient ices under pressure for billions of years are beginning to wake up. Buried within this ancient visitor are volatile compounds that have been building pressure for 7 billion years. And solar heating could trigger explosive releases comparable to nuclear weapons. Comet outbursts rank among the most violent events in our solar system. When subsurface pockets of volatile materials suddenly vaporize, they can increase a comet's brightness by thousands of times within hours. The explosive force literally blows away surface material, exposing fresh ice to solar radiation and creating cascading chain reactions. This visitor carries outburst potential, unlike anything previously observed. 7 billion years of cosmic ray bombardment has created exotic chemical compounds and crystal structures that exist nowhere else in the known universe. These materials have been subjected to pressures and temperatures that could create highly unstable configurations. The chemical composition analysis reveals particularly concerning concentrations of carbon dioxide, carbon monoxide, and carbonyl sulfide. These compounds can exist in solid form under extreme cold, but rapid heating causes them to expand explosively. The visitor's unusual chemistry suggests much higher concentrations than typical comets. Consider the energy storage involved. Every molecule of frozen gas represents potential kinetic energy waiting to be released. After billions of years of accumulation, the total stored energy could rival the explosive force of major volcanic eruptions or large meteor impacts. Surface mapping attempts have revealed irregular brightness variations that suggest active venting is already occurring. As solar heating increases, these small releases could escalate into major outburst events that fundamentally change the visitor's structure and trajectory. The exotic metallic compounds detected in the comet's atmosphere add another explosive element. Atomic nickel and other heavy elements require extreme temperatures to vaporize, suggesting internal heating processes are already active within the nucleus. Such heating could trigger outbursts without additional solar input. Outburst events typically follow unpredictable patterns. A comet might remain relatively quiet for months before suddenly brightening by a factor of 10,000 in a matter of hours. The trigger mechanisms often involve subsurface cave-ins that expose large areas of fresh ice to space simultaneously. Historical comet observations show that first-time visitors to the inner solar system exhibit the most dramatic outburst behavior. Objects making their initial close approach to the sun often undergo multiple explosive events as different layers of material reach vaporization temperatures. This visitor faces thermal shock far exceeding anything experienced by solar system comets. The temperature differential between 7 billion years at near absolute zero and intense solar heating could cause explosive expansion that tears the nucleus apart from within. The outburst debris would travel at the same hyperbolic velocities as the parent object, creating high-speed projectiles that could pose threats across vast distances. Unlike normal comet debris that follows predictable orbital patterns, these fragments would scatter on trajectories impossible to calculate in advance. Multiple outburst events could create a debris field extending across millions of miles, with individual fragments following independent hyperbolic paths out of the solar system. Any spacecraft or celestial body intersecting such a field would face bombardment by projectiles traveling faster than any human-made object. The chemical composition of outburst material poses additional hazards. The toxic gases detected in the comet's current atmosphere would be released in concentrated form during explosive events, creating pockets of contaminated space that could persist for years. Timing predictions for outburst events remain impossible with current technology. The explosions could begin at any point during the solar approach, occur multiple times during perihelion passage, or remain dormant until the comet begins its outbound journey. But explosive outbursts are not the only danger this visitor poses during its most critical phase. We are about to lose sight of it at the worst possible moment. For several critical weeks during perihelion passage, this visitor will disappear behind the sun precisely when it poses the greatest threat, leaving us blind to catastrophic changes. Solar conjunction represents every astronomer's nightmare scenario. When an object passes directly behind the sun from Earth's perspective, all ground-based telescopes and most space-based instruments become completely useless for observation. We lose our ability to track its position, monitor activity, or detect any changes in trajectory or behavior. This blackout period could not come at a worse time. Perihelion passage represents the moment of maximum thermal stress, highest outgassing activity, and greatest fragmentation risk. Everything dangerous about this visitor will reach peak intensity precisely when we cannot observe what is happening. The blind spot duration depends on several factors, including the object's brightness, solar interference levels, and telescope capabilities. Current predictions suggest a blackout lasting anywhere from 2 to 6 weeks, during which the visitor will be completely invisible to human observation. Consider what could occur during this critical period. Fragmentation events, major outbursts, trajectory changes, or complete disintegration could happen without any warning or documentation. The visitor that emerges from behind the Sun in December might be completely different from the object that disappeared in October. Space-based telescopes positioned at different orbital locations might provide limited observation capabilities, but none can maintain continuous tracking during solar conjunction. The James Webb Space Telescope, Hubble, and other major instruments all face the same fundamental problem. They cannot point directly at the Sun without suffering permanent damage. NASA scientists have discussed emergency protocols for repurposing existing spacecraft to observe the visitor from different vantage points. But current missions lack the necessary orbital positions or instrument capabilities. The Parker Solar Probe operates closest to the Sun, but was not designed for comet observation and would face its own operational challenges. The European Space Agency's Solar Orbiter mission offers some potential for observation during parts of the conjunction period, but its instruments focus on solar physics rather than comet composition and behavior. Adapting these systems for visitor tracking would require significant operational changes. Ground-based radio telescopes might maintain some tracking capability during the early and late phases of conjunction, but radio observations provide limited information about physical changes or fragmentation events. Visual and infrared observations remain impossible throughout the core blackout period. The timing creates cascading problems for post-conjunction reacquisition. When the visitor emerges from behind the Sun in early December, astronomers will need to relocate it quickly to resume tracking. If major changes occurred during conjunction, this could prove extremely challenging. We could be tracking a completely different object or a debris field without knowing it. The potential for significant alterations in the visitor's trajectory or fragmentation during the blackout period means that our last confirmed location from October might be completely irrelevant in December. This creates an observation gap that could have consequences we cannot yet foresee. The visitor's speed and hyperbolic trajectory mean that any changes during conjunction would be amplified over interstellar distances, making it nearly impossible to predict where the object or its fragments might be heading. But the blackout is just one problem we face. The real threat is the permanent danger this ancient object leaves behind for future generations. We are about to be hit with a cosmic cocktail of toxic gases that could contaminate the solar system for years. The visitor's chemical composition and active outgassing process pose a significant contamination threat to our solar system's environment. This ancient object's internal structure contains volatile compounds that have been frozen solid for billions of years. The chemical signature of the gas and dust streaming from the comet contains a toxic cocktail of carbon dioxide, carbon monoxide, and cyanide gas. This atmosphere is more poisonous than anything found in our solar system's natural environment. As the visitor travels through space, it continuously releases these chemicals, creating a vast cloud of contamination that follows its trajectory. The comet's coma extends for hundreds of thousands of miles, meaning that any spacecraft passing through its vicinity would be exposed to a poisonous atmosphere that could degrade instruments and pose risks to future human exploration missions. The contamination threat becomes even more significant if the visitor fragments during perihelion passage. Each fragment would become a new source of contamination, releasing its own pocket of toxic gases into the solar system. This would create a widespread debris field of poisonous materials that could persist for years, making certain regions of space unsafe for travel or exploration. Unlike cometary debris that disperses over time, the hyperbolic trajectory of these fragments ensures they will remain in unstable orbits, periodically bringing contamination back into the inner solar system. The chemical makeup of the contamination poses a serious hazard to scientific instruments and human health. The presence of metallic vapors, like atomic nickel, suggests that the contamination could also be corrosive, degrading spacecraft surfaces and sensitive equipment. The cosmic ray bombardment that the object has endured for 7 billion years might have also created new and unknown compounds within its structure. When these exotic materials are released during outgassing events, they could introduce chemical agents that our current planetary defense systems are not equipped to handle. The contamination is not limited to gaseous chemicals. The outgassing process also releases solid particles, ranging from microscopic dust to chunks of ice and rock. These fragments, traveling at interstellar velocities, would carry the same toxic chemical signature and could contaminate any celestial body they impact. A collision with Mars, for example, could introduce poisonous materials into the Martian environment, contaminating surface areas and subsurface ice deposits. The long-term effects of this contamination are unknown. The persistent nature of the debris field means that the visitor's influence on our solar system will last long after it has disappeared into deep space. Future missions to Mars, the asteroid belt, and the outer planets will need to take this contamination threat into account, potentially requiring new shielding technologies or navigation protocols to avoid hazardous regions. The toxic atmosphere and chemical contamination demonstrate that interstellar visitors can pose biological threats to life forms throughout our solar system. The cosmos contains materials and process that could render planets uninhabitable or destroy ecosystems that took billions of years to develop. Our spacecraft and space-based infrastructure remain vulnerable to threats moving at velocities that overwhelm existing protection systems. The democratization of space access has created hundreds of potential targets for destruction by objects we cannot track or defend against. The limited observation window reveals that humanity often gets only one chance to study cosmic phenomena that could answer fundamental questions about the universe's structure and evolution. Scientific opportunities lost to weather, equipment failures, or scheduling conflicts may never return. The visitor's eventual departure will carry away more questions than answers, reminding us that the universe operates according to principles and timescales that exceed human comprehension. We remain newcomers in a cosmos filled with ancient mysteries that may be impossible to solve. This encounter has taught us that Earth exists, not in isolation, but as part of a dynamic and potentially dangerous galactic community, where 7-billion-year-old visitors can arrive without warning, challenge our understanding of reality, and disappear again into the void between stars. We are not alone in the universe, and we are not safe. The most disturbing revelation comes from an unexpected source. Astronomers have detected radio echoes from the visitor that suggest it is an artificial construct rather than a natural comet. When scientists performed ground-based radar scans of the approaching visitor, they expected to receive a faint echo consistent with a solid, irregularly shaped object. Instead, they detected a highly structured signal that seemed to be actively managed. The echoes were not random, but instead displayed a geometric regularity that is impossible to achieve with a natural object. The signals were not from communication, but rather a form of active sensing, like a sonar system. The echoes pulsed outward from the object in a regular pattern, mapping the space ahead of it and detecting potential obstacles. This discovery provides compelling evidence for the visitor's artificial origin. A natural object would not generate such a regular, directional signal. The echoes were also detected across a broad range of frequencies, something that a single piece of space junk or a natural object would not be able to do. The echoes themselves were not just reflections of the radar signal. but seem to be remodulated and amplified by the visitor's internal systems. This suggests an active transponder or a powerful internal power source. The presence of an active radar system on the visitor points to a technological purpose: navigation. An interstellar object traveling at such high velocity would require sophisticated navigation capabilities to avoid collisions with microscopic particles, let alone asteroids or planets. The echoes reveal that the visitor is actively scanning its environment and making real-time course corrections. The implications of this discovery are staggering. If this is an alien probe, it is not a dead, inert rock. It is a living, thinking machine, actively aware of its surroundings and its position in space. The fact that it is silently moving through our solar system, actively scanning its environment, suggests it is on a reconnaissance mission. It is gathering data about our planet, our sun, and our technological capabilities. It has been doing this for billions of years, and now it is finally here. The radar echoes from the visitor are not a threat in themselves, but they are a warning. They are proof that we are not alone in the universe, and that other civilizations are far more advanced than our own. The active radar system also explains the visitor's anti-tail, the forward-streaming particles that defy the laws of physics. The radar signal, which is a powerful burst of electromagnetic energy, could be ionizing and accelerating particles from the comet's surface. This would create the forward-streaming tail we see, but it would not be a natural phenomenon. It would be a side effect of the alien probe's active navigation system. The radar pulses could be deliberately timed to release particles in a specific direction, creating a kind of artificial shield or a decoy system. This would explain why the particles are so large and why they resist solar pressure. They are not being pushed by solar wind, but rather being ejected by the probe's internal systems. The anti-tail is not a natural phenomenon. It is a technological marvel. But the most chilling possibility is that the visitor is not a probe, but a seed. What if this is an ancient form of terraforming technology, designed to transform planets into habitable worlds for its creators? The toxic cocktail of chemicals in its atmosphere, which is so dangerous to humans, might be a deliberate part of this process. The cyanide gas, for example, is a powerful poison for Earth-based life, but it could be a crucial nutrient for a completely different kind of life form. The fact that the visitor's atmosphere is dominated by carbon dioxide suggests that its creators might be a carbon dioxide-breathing species, for whom our own atmosphere would be a deadly poison. The high concentrations of carbon monoxide could be used to create building blocks for new life forms, while the atomic nickel vapor could be a source of essential minerals for a metallic-based biology. If this is a terraforming seed, it could be a sign that we are in danger. The visitor's arrival coincides with the moment when Earth is finally reaching a level of technological sophistication that could be a threat to its creators. What if the goal of this mission is to eliminate humanity and prepare the planet for a new kind of life? The visitor's passage through our solar system is a kind of test. It is a way for the alien probe to gather data about our planet, our atmosphere, and our ability to defend ourselves. If we show no sign of being able to stop it, the probe could activate its primary function: to release its toxic payload and begin the process of terraforming Earth. The visitor's journey through our solar system is a cosmic experiment. We are the test subjects, and the visitor is the laboratory. It is observing our every move, measuring our every reaction, and gathering data that will be used to determine our fate. If we fail to stop it, we will be replaced. The ancient wanderer from the galactic thick disk is not just a scientific curiosity, It is a harbinger of a new kind of war. A war not of armies and weapons, but of biology and chemistry. A war for the survival of two species, one ancient and one new. The countdown has already begun. The visitor's speed and stealth capabilities suggest its builders intended for it to be a secret. A reconnaissance mission designed to fly under the radar, gathering intelligence without revealing its artificial nature. The lack of any radio emissions, despite the visible outgassing and particle production, is a clear sign of sophisticated stealth technology. Advanced civilizations would prioritize electromagnetic stealth for interstellar reconnaissance missions. Radio silence prevents detection by target civilizations while allowing the probe to gather intelligence without revealing its artificial nature or origin. The visitor's chemical composition produces ionized gases that should create natural radio emissions. Yet sensitive radio telescopes worldwide detect nothing above background noise levels. This suggests active suppression technology rather than passive electromagnetic invisibility. Stealth spacecraft design would incorporate materials and geometric configurations that absorb or deflect electromagnetic radiation rather than reflecting it back toward potential observers. The visitor's surface properties appear optimized for such electromagnetic management. The lack of thermal radio emissions indicates sophisticated heat management systems that prevent waste energy from escaping indetectable frequencies. Natural objects experiencing solar heating typically radiate excess energy across broad electromagnetic spectra. Military radar systems designed to track stealth aircraft have been unable to obtain clear returns from the visitor despite its substantial size and metallic particle emissions. This suggests technology specifically designed to defeat electromagnetic detection systems. The visitor's hyperbolic trajectory would be ideal for passive electromagnetic reconnaissance, allowing comprehensive scanning of our solar system's radio emissions while maintaining electromagnetic silence to avoid counter-detection. Earth-based radio telescopes have monitored the visitor continuously across multiple frequency bands, searching for any electromagnetic signatures that might indicate an artificial origin. The complete absence of detectable emissions exceeds statistical probability for natural objects of this size and activity level. The electromagnetic silence becomes more remarkable when compared to other interstellar visitors. Previous interstellar objects produced detectable radio emissions consistent with natural outgassing and heating processes, making this visitor's silence anomalous. Advanced signal processing techniques designed to detect weak emissions from deep space objects have found no electromagnetic signatures associated with the visitor's position or trajectory, despite clear evidence of active material production and release. The visitor's approach from the galactic thick disk region would provide optimal positioning for long-range electromagnetic surveillance of our solar system's communication networks and technological development. Radio astronomy facilities worldwide have coordinated observation campaigns specifically to search for any electromagnetic evidence of artificial systems aboard the visitor. The universal failure to detect emissions suggests deliberate technological countermeasures. The electromagnetic silence extends across all frequency ranges, from radio waves through infrared to visible light, indicating comprehensive stealth technology rather than selective frequency suppression. Such sophisticated electromagnetic management requires advanced materials, science, and power systems that exceed current human technological capabilities by substantial margins. The combination of electromagnetic silence with active particle production and chemical outgassing represents technological sophistication that would be impossible to achieve with natural processes alone. But the visitor's stealth capabilities raise disturbing questions about its origins. The region of space it comes from holds secrets about the earliest epoch of cosmic evolution. This ancient wanderer originates from the galactic thick disk, a region populated by the oldest stars in our galaxy, formed when the universe was young and the laws of physics operated under different conditions. The galactic thick disk represents our galaxy's ancient foundation, containing stars that formed over 10 billion years ago when the Milky Way was still young and chaotic. These stellar ancestors condensed from primordial gas clouds, enriched by the very first generation of massive stars that ended their lives in spectacular supernovae. Tracing the visitor's trajectory backward through space and time reveals its origin in this ancient stellar neighborhood. The hyperbolic path, when projected into the past, leads directly to regions dominated by thick disk stars with chemical compositions and ages that predate our sun by billions of years. Stars in the thick disk formed under conditions that no longer exist anywhere in the observable universe. The early galaxy contained different ratios of heavy elements, operated under different gravitational dynamics, and experienced violent merger events that scattered stellar materials across vast regions. The chemical signatures detected in the visitor's atmosphere match theoretical predictions for materials processed by thick disk stars. The exotic ratios of carbon dioxide, metallic vapors, and trace compounds could only form in the nuclear furnaces of these ancient stellar giants. Thick disk objects represent time capsules from cosmic dawn, preserving materials and processes from the universe's first billion years, when galaxy formation was violent and chaotic. Any comet originating from this region would contain isotopic signatures impossible to replicate in modern stellar environments. The 7 billion year age estimate places the visitor's formation during the galactic thick disk's most active period, when massive star formation rates created supernovae explosions that enriched the interstellar medium with heavy elements at unprecedented rates. The preservation of such ancient materials in solid form suggests the visitor formed in regions of space where temperatures and pressures allowed exotic ice formation under conditions that modern astrophysics struggles to model accurately. Thick disk stars follow highly elliptical orbits that carry them far above and below the galactic plane, creating opportunities for planetary system disruption that could eject comets on interstellar trajectories at the velocities observed in this visitor. The gravitational dynamics of the early galaxy were fundamentally different from current conditions. Massive dark matter concentrations and ongoing merger events created chaotic environments where planetary systems could be violently disrupted, flinging their comet populations into interstellar space. Computer models of galactic evolution suggest that trillions of objects were ejected from thick disk stellar systems during the galaxy's violent youth, creating a vast population of interstellar wanderers that have been traveling through space for billions of years. The visitor represents our first opportunity to study materials from this ancient epoch directly. Unlike light from distant galaxies, which shows us only surface conditions, this object carries actual physical samples of matter processed by the universe's first stellar generations. The thick disk origin explains the visitor's remarkable durability and exotic composition. Objects formed in such extreme environments would necessarily possess properties that allow survival across cosmic timescales under conditions no modern comet ever experiences. The trajectory suggests the visitor has been traveling for roughly 7 billion years since its ejection from the thick disk region, making it potentially the oldest intact object ever observed in our solar system. The implications of thick disk origin extend beyond mere scientific curiosity. These ancient stellar regions could harbor civilizations that have had billions of years longer than humanity to to develop advanced technology and expand across the galaxy. If the visitor represents technology from a thick disk civilization, its builders would possess technological capabilities developed over timescales that dwarf human history. Such civilizations could have achieved interstellar travel when our solar system was still forming. But the thick disk origin raises the most disturbing question of all. What other ancient visitors might be heading our way from this cosmic graveyard? Every second this visitor travels through space, it sheds thousands of particles that could create permanent navigation hazards lasting centuries after its departure. The continuous outgassing process releases not just toxic gases, but solid particles ranging from microscopic dust to chunks of ice and rock several feet across. At the visitor's hyperbolic velocity of 61 kilometers per second, these fragments become high-speed projectiles that follow independent trajectories through the solar system. Unlike debris from solar system comets, which eventually settles into predictable orbital patterns, particles from this visitor maintain their interstellar velocities. This creates a debris field composed of fragments traveling too fast to be captured by solar gravity, yet moving slowly enough, relative to the parent object, to spread across enormous volumes of space. Computer simulations suggest the debris field will continue expanding for decades after the visitor's departure. Individual particles will follow slightly different trajectories based on their size, composition, and the exact timing of their release from the nucleus. The largest fragments pose the greatest navigation hazards. Chunks of ancient ice measuring several meters across could destroy any spacecraft unfortunate enough to intersect their paths. Unlike natural meteoroids that burn up in planetary atmospheres, these fragments carry enough mass and velocity to penetrate any existing defensive systems. The debris distribution follows the visitor's hyperbolic trajectory, but spreads into a cone-shaped region, extending millions of miles behind the object. This expanding cone will intersect multiple spacecraft routes, satellite orbits, and planetary approach corridors used by current and future missions. Tracking individual debris particles presents enormous technical challenges. The fragments are too small for most telescopes to detect individually, yet large enough to cause catastrophic damage to spacecraft. This creates invisible minefields that could persist throughout the inner solar system for years. The exotic composition of the debris adds another layer of complexity. Particles containing the visitor's unusual chemical mixture could contaminate any surfaces they impact, creating toxic hotspots on asteroids, moons, or spacecraft that encounter the debris field. Fragment velocities vary depending on the outgassing dynamics at the time of release. Particles ejected during high activity periods could be moving significantly faster than the parent object, while those released during quiet periods might trail behind at slightly lower speeds. The debris field will be densest along the visitor's exact trajectory, but could extend hundreds of thousands of miles to either side, depending on the angular momentum imparted during particle release. This creates a hazard zone much larger than the visitor's immediate vicinity. Solar radiation pressure affects different particles differently, causing gradual spreading of the debris field over time. Smaller particles get pushed farther from the original trajectory, while larger fragments maintain courses closer to the visitor's path. Current space traffic control systems were not designed to track debris moving at interstellar velocities. Existing orbital debris monitoring focuses on objects in Earth orbit, traveling at much lower speeds with predictable trajectories. The debris field could interfere with planned missions to Mars, the asteroid belt, and outer solar system destinations. Spacecraft would need to adjust their routes or timing to avoid intersecting the contaminated regions, potentially delaying missions by months or years. Some fragments might achieve sufficient velocity to escape the solar system entirely, carrying samples of the visitor's exotic materials to other star systems. These particles could seed interstellar space with contamination that affects future travelers between the stars. The permanent nature of the debris field means the visitor's influence on our solar system will persist long after the object itself disappears into deep space, creating lasting consequences for space exploration and planetary defense. But the greatest immediate threat comes from active spacecraft that cannot avoid the expanding debris field. Multiple billion-dollar space missions currently operating throughout the solar system face destruction from invisible debris traveling at speeds that would vaporize any protective shielding. NASA's Parker Solar Probe, designed to study the sun's corona, follows an orbital path that could intersect the visitor's debris field during its closest solar approaches. The probe's heat shields were designed for solar radiation, not high-velocity impacts from exotic ice and rock fragments. The European Space Agency's Solar Orbiter mission faces similar risks. Its trajectory carries it through regions where the visitor's debris could create a gauntlet of high-speed projectiles. Even particles smaller than a grain of sand could penetrate the spacecraft's protective systems at interstellar velocities. Mars-bound missions represent particularly vulnerable targets. The visitor's trajectory passes directly through the orbital zone of the red planet, creating maximum debris density along routes used by current and future Mars explorers. The Mars Sample Return mission, years in development, could be destroyed before completing its primary objectives. Europa Clipper, humanity's ambitious mission to explore Jupiter's ice-covered moon, launches directly into the timeframe when debris hazards will be at their peak. The spacecraft's delicate instruments and solar panels cannot survive impacts from particles traveling at 60,000 miles per hour. The James Webb Space Telescope, positioned at the L2 Lagrange point, faces threats from debris that could disable its primary mirror or sensitive instruments. A single impact from a fragment the size of a marble could end a mission that cost $10 billion and took decades to develop. Current spacecraft shielding technology provides protection against typical space debris traveling at orbital velocities of a few miles per second. The visitor's fragments move 30 times faster, carrying kinetic energy levels that overwhelm any existing defensive systems. The invisible nature of the debris makes avoidance maneuvers impossible to plan. Unlike trackable objects that can be predicted and avoided, the visitor's particle field contains millions of fragments too small to detect, but large enough to cause catastrophic damage. International space agencies have no protocols for managing debris moving at interstellar speeds. Emergency procedures designed for orbital debris assume objects traveling at predictable velocities along known trajectories, not hyperbolic fragments scattered across millions of miles of space. The timing could not be worse for commercial space operations. Private companies have invested billions in satellite constellations, space stations, and lunar missions that could all face destruction from untraceable debris. Insurance companies have no models for calculating risks from interstellar contamination. Robotic missions throughout the solar system lack the capability to detect approaching debris and execute evasive maneuvers quickly enough to avoid high-speed impacts. Most spacecraft operate on predetermined flight plans that cannot be rapidly modified to address new threats. The debris hazard extends beyond government and commercial missions to affect amateur radio satellites, university research projects, and international cooperative ventures. The democratization of space access has created hundreds of potential targets that lack sophisticated protection systems. Ground-based space surveillance networks designed to track orbital debris cannot effectively monitor objects moving at interstellar velocities. The detection systems and prediction algorithms work within parameters that do not account for hyperbolic trajectories. Some spacecraft might survive initial debris impacts, but suffer degraded performance that compromises mission objectives. Solar panels riddled with microscopic holes, communication antennas damaged by particle strikes, or navigation systems disrupted by electromagnetic interference could end missions prematurely. The cascading effects of multiple spacecraft losses could set back space exploration by decades. Scientific missions representing years of development and billions of dollars in investment could be destroyed in seconds by invisible fragments from an ancient visitor. But even if our spacecraft survived the debris field, we face another critical limitation. The narrow window for studying this visitor is rapidly closing forever. Humanity has less than 3 months to gather data about this ancient visitor before it disappears forever, and critical observation opportunities are already being lost to weather, technical failures, and orbital mechanics. The visitor's hyperbolic trajectory ensures this is a once-in-a-lifetime scientific opportunity. Unlike periodic comets that return every few years or decades, this object will never come back. Every day of lost observations represents irreplaceable data that could have answered fundamental questions about the early universe. Weather patterns across the globe have already interfered with crucial observation windows. Cloud cover has prevented ground-based telescopes from conducting spectroscopic analysis during periods of peak activity, while atmospheric turbulence has degraded image quality needed for precise measurements. Technical failures have plagued multiple observation campaigns. The Hubble Space Telescope experienced pointing system glitches during scheduled observation periods, while ground-based facilities have suffered equipment malfunctions at critical moments when the visitor was displaying unusual behavior. The visitor's rapid motion across the sky creates scheduling conflicts between different research teams. Telescope time is allocated months in advance, but the object's unpredictable activity levels mean that predetermined observation schedules might miss the most important events. International coordination has proven challenging, as different observatories operate under varying administrative systems and scientific priorities. While some facilities focus on trajectory measurements, others prioritize compositional analysis, leading to gaps in comprehensive data collection. The approaching solar conjunction represents the most significant loss of observation time. For several weeks, during the visitor's closest approach to the Sun, no Earth-based instruments will be able to track its behavior during the period when thermal stress could trigger the most dramatic changes. Space-based telescopes face their own limitations. The James Webb Space Telescope can only observe the visitor during specific orbital positions, while Hubble's aging systems require careful scheduling to maximize scientific return from limited observation windows. The discovery of this visitor has sparked a renewed sense of urgency among the scientific community. Researchers are now working around the clock to coordinate observations, share data in real time, and develop new analysis techniques to extract as much information as possible from the limited window we have. The race to study this ancient object is a race against time itself. Every hour that passes brings the visitor closer to its perihelion passage and its eventual departure from our solar system. This encounter reminds us of the fleeting nature of cosmic opportunities and the importance of global cooperation in the face of universal mysteries. The secrets this visitor holds could fundamentally change our understanding of the universe. But if we fail to act quickly, they will be lost to us forever. Now is the moment for Stellify science. We must transcend our limitations and work together to unlock the secrets of the cosmos. Join us in this cosmic quest, where every discovery is a step closer to understanding our place in the universe. Don't let this once-in-a-lifetime opportunity slip away.